is kind of followed mechanically. It's, I guess, something you might do in the military where you do this first, then you must do this second, and everything gets done. So, first thing a hypothesis test consists of, and I'm just putting the headings down and then we'll do an example, is you state the hypothesis. We'll go into what that means later. And the second step is you collect the statistics. The third step is you find a guy called the p-value. And the final step is conclusion. So what we're going to do today is we are going to go through those 4 steps with a variety of stories, and each time that we do it, we're going to look at you know, a hypothesis test from start to finish, and hopefully that'll give us a good idea of how this process works, because essentially that's what it is. It's a process, a very special process. Everyone in statistics does it the same way. So if you wanted to prove anything in a statistical way, so if you ever hear something that says, oh, there, I'm trying to think of the phrase now. Got it written down here. There we go. If you ever hear anything and it says it's statistically significant, it will have came from this process. So you know how they'll say sometimes that it's now been proven that A is bigger than B, or people live longer in the past than they do in the future, or whatever it is they come up with. And they will say that this is statistically significant result. And we will be able to look at this and hopefully everybody can agree that whatever conclusion you came to, they all come to the same conclusion. So here's our first example. Let's assume that back in the day, the average height of Scottish people was 63 inches. And they probably would get that by just looking at skeletons and measuring. If you know the full skeleton, I think you can tell what height that adult male would be. So we'll make this the average height of a male Scot. And it's 63 inches tall. And this, I think it's anthropologist, yes, this anthropologist thinks that today's people, today's Scottish people, are taller than they were in the past. But he has to prove that to the other anthropologists in particular. Now, it may be something that's kind of obvious, but he's not allowed to say, well, I live in Edinburgh and I walk around and I see a lot of people and most of them are bigger than 5'3", so there's my evidence, because that's anecdotal evidence. Anecdotal evidence is very, very low down in the food chain, right? You can't really use that as proof. So we have to go and we have to figure out a much more structured way, and it's called the hypothesis test, to prove something. So we're going to start off with step 1, which is state the hypothesis. And you're going to have 2 guys. The first one is called the null hypothesis. In this case, the null hypothesis is that the mean of the population of adult Scots males is still 63. In other words, it's the same thing that it used to be. Still 63 then, still 63 now, nothing's happened, right? Now the alternate depends on what that social anthropologist has decided. Now in my story here, didn't he think that it had increased? So the alternate hypothesis, which is this one, is in this case, it's mu greater than 63. So we're going to do a comparison. Population mean is 63. Population mean is now bigger than 63. And hopefully we can find enough evidence to prove this. And if we can, you would publish the results. Now, every hypothesis test, I can't say it, significant level, called alpha. Now, the significance level alpha is what percentage of the time are you willing to get this process wrong? So it typically falls into 3 categories. A significance level of 10%, a significance level of 5%, and a significance level of 1%. One of those 3 will be chosen in each question. You don't choose them. When you read the question in your homework, they will tell you alpha equals 0.05 or alpha equals 0.01. It is called the significance level. So that's the start. Number 1, describe or state the hypothesis. The null hypothesis, sometimes called H0, is that the mean is still 63. The alternate in this story is greater than 63. So what does that person do? Well, he would go to his university and say, I need some money. And they'll say, what do you need the money for? I want to do a survey of modern adult Scots males because I've got a feeling that they're taller now than they used to be in the past. And then I'm going to write a paper and I'm going to publish it in Anthropology journal. And you know, universities, one of the ways universities get prestige is by the number of papers that get published in peer review magazines, right? The bigger the better, and the more the merrier, right? So the university does have a kind of motivation to, you know, to be known as a research university, right? Because this is research. Not very clever research, I agree, but it still counts. So he gets some money, and with his money, he manages to get a sample of 300 randomly selected adult males. Has to be a good random sample the usual way. And he finds out that the average height is 64 inches. And now I'm going to add a little bit that isn't true most of the time, but we'll assume that it is this time. That we know sigma. So it's actually going to be told up here. You'll be told sigma equals something, right? And we're going to figure out that in this case, sigma equals 2, right? It's just a little unlikely, but it is. So, oh. So far, so good. So that is almost step 2 done. I've collected the statistics. There's one new guy I need to get. Well, 2 new actually. This fella here, and I'm going to get a guy called the standard error because this fella here is going to use it. And the standard error is given by that formula. Put a little dotted line there, right? Can you remember the standard error formula from a way back when is it? When we did confidence intervals. Can you remember those guys? Right? It's called the sampling distributions. Standard error is another name for it. Now, in this case, because we know that's 2 and we know that that's 300, we're going to come up with hopefully a pretty small number. So 2 divided by the square root of 300. And the answer we get is 0.115. So far, so good. Now, This Z is your Z score, and the formula for getting this particular Z score is going to be try again. It's going to be this guy. Basically, data take away the mean over standard error. Now, in this case, X bar is 64, and there's a funny little cryptic guy here called mu naught. Mu naught is what we call this number here. So in this case, 63. And the whole thing is going to be divided by the standard error, 0.115. And then I go to my calculator, and put a little bracket. I'll do 64, take away 63, which I really didn't need to do, it's 1, divided by 0.115, and we come up with a Z of 8.7 roughly. So that is what step 2 is going to look like. The statistics, the 300, the X bar, the standard error, and then basically culminating in this fella here. Okay, that's step 2. Step 3, find the p-value. Now let me return to this fella here for a minute. We got this fella is 63, right? And we've got the alternate, which is it's greater than 63. If you draw the normal Z distribution of this guy, would you agree that 8.7 is very extreme? In fact, typically, what kind of numbers do you need to be unusual Z scores? I mean, 8.7 is really extreme, but what kind of numbers do you need to become, oh, that's kind of big. It's kind of unusual. That doesn't happen often.
-3 plus 3,
yeah. Right. So just like a signpost, can we pretend 3's a bit here? So who is this p-value that we're about to calculate? Well, the p-value is the probability that you get a Z score greater than that one. Essentially, the p-value is, what's the probability that you got this data if that was true, right? So if the population mean was 63, what's the chances that you could get an average of 64, right? And that number, this p-value, if it's really, really tiny, what that is saying is that's not really likely that that happened. This is much bigger than that. This is so big that that's wrong, right? It's so unlikely that this happened just by chance and that was true. So it's a kind of, you prove something by proving how unlikely the opposite is. If it's 1 billion to 1 chance that I'm English, would you agree the chances are I'm not English? It's kind of that logic, right? If the chance of something happening is extremely tiny, then the assumption that you made at the beginning is not true. That's kind of the logic behind it. So if we look at this fella, we are going to have to find the probability that a Z score is greater than 8.7. Agreed? So where is this guy hiding? Can anybody remember where that one was? And he's not in stats. Imagine this is the final and you got this question. You're going to be panicking right now as you try and rush through all your notes to try and find a piece of notes that mentioned it. Last chance before I tell you. Where do you find the probability that a z-score is bigger or less than a number? Which calculator menu does that?
Isn't it under distribution?
You just made it. Yes, it is. And which one? Number 1 or 2? I guess it could be 3, 4, 5, but nobody uses anything after 3. So 1 or 2?
Number 2, this normal CDF.
Right, and so we type that normal CDF, so I'm going to put that in now, so that when you look at your notes, you can kind of hopefully see where that is. Normal CDF. I guess I'll put over here, kind of cryptically. Second distribution, right? Just in case you have to remember where it is. Now, if you want to be bigger than 8.7, remember those 4 numbers in this thing? Little guy, big guy, 0 and 1, right? Little guy, big guy, mean and standard deviation. In this case, mean is 0 and standard deviation is 1. So it's going to be 8.7 and somebody bigger than it, mean of 0, standard deviation of 1. What magic number do I put in, oops, here in the second position?
999.
See, that's stuck. Followed by a 0, followed by a 1, close the whole thing off, and we are looking at 1.7 e to the negative 18. Now, a z-score of 8.7 is, do you know you could win the lottery a couple of times in a row and it probably still wouldn't be that number. That's how unlikely this is. But that's what the calculator says, but that's not good math. Would you agree it's that guy? Now, don't do this because I'm not going to do it. Isn't it 18 zeros and then a 17 if you wanted to write it out in full? For all practical purposes, isn't that essentially negligible? Almost 0 to the point that it doesn't matter, right? So that is step 3. Step 4, conclusion. Well, the conclusion is based on this test. This is what you check. I'll put it in red. You ask the question, is the p-value less than alpha? Now, in this story, the p-value was this horrible guy. And it's less than alpha, and I think I may not have just told you this one, but I decided right at the start that that was going to be the alpha in the question. So the question is this guy less than that guy? Well, is he? Is this number less than that number?
Significantly.
Definitely, without argument. So if you say yes, is this less than that? You would say yes, significantly. You can then say the following. This is a statistically significant result. What this has said is p-value. The probability of you getting this sample using that as the reality is so unlikely that this cannot be true. So the standard sentence that you do when you come to this conclusion, right, that the p-value is less than alpha, and that means we have a statistically significant result, is you write this down. There is enough evidence to reject H naught. I did say not. One of my classes thought I said something else, like not as in K-N-O-T. This is old-fashioned not as in zero. Some of you know not as zero, don't you? N-A-U-G-H-T. Two of you know that. Okay. Read your Shakespeare. I care not of that man. Means I care nothing of. Right. Okay. There is enough evidence to reject H naught, and so HA is true. Now that's the statistical way of saying we have just convicted you of the crime of being bigger than 63. The chances that you got this data and you did not commit the crime are so small, you must have committed it. So you could say in English, which you probably would, I have now proved statistically significant result that Scottish people of today, adult Scottish males of today, are taller than they were in the past. And it's the kind of evidence that a French scientist could look at, a German scientist, a Rwandan scientist, no matter where in the world they live. We followed this very precise procedure. It's called the hypothesis test. This is the process. And because we all follow this process and we've all agreed how it should be done, and we've all agreed that when you get a statistically significant result, you then have to accept it. Okay, I guess Scottish people are bigger today than they were in the past. And maybe that will open itself up into quite interesting areas of research of what always strikes me as, and the classic thing is, once you know something is true, at least the statistical sense is true, don't you then ask yourself why? Why are Scottish people taller today? And that can be very often more interesting. Agreed? Cool. Now, let's give you some names. To see this particular story, we were looking for evidence that the mean had changed. It was bigger than it used to be. When you do that kind of story, there are many names for it. I'm going to call this one a right-tailed test. And the reason it's called a right-tailed test is, can you remember over here, we're trying to find the area of that little tail to the right, the right-hand tail? That was it. Right, anything about this process? Because I'm going to spend the first part of today just doing examples of this and proportion examples of this. Is there anything, are we good, at least the first one? Right, so it's going to be a story. That's going to lead to step 1, 2, 3, 4, and at the end we can have a conclusion. What might happen then if the conclusion here was that this wasn't true? Can you imagine I got a p-value, I know, of 0.4, right? Let's say we did all this and this answer here came out as 0.4. Then when I did the test, is the p-value less than alpha? Is 0.4 less than 0.1? We'd say no, right? That's the only other choice, right? The answers to that question, you know, the conclusion question, isn't it always going to be no or yes? It's got to be one or the other. If it's no, then this is not, so you stick the word not, a statistically significant result. And what's the conclusion? There is not enough evidence to reject H naught. What does that mean in real life? You've just spent a couple of weeks of your life and not found anything useful at the end of it. The sample has not came up with any evidence that something unusual is going on. It would mean, I guess, that there's no evidence to show that Scottish people of today are taller than they were in the past. It doesn't mean that we are sure that we're still 63 inches. It doesn't mean that. It just means there's no evidence to prove that we're not 63. That's not the same as there is evidence to prove we are 63. analogy. Couldn't a person commit a crime, but we don't have evidence enough to convict them? So you might say, there's not enough evidence to convict that person. That's not the same as saying that person didn't commit the crime. Right? So it's kind of lawyer-esque, but that's how we do it. So that was an example of a story involving mean standard deviation none. Let's do our next story. What should we do? Trying to think of one. Somewhere reduction. Oh, darn it, my brain's freezing up here. I need to find a story where something is reducing. Has anybody got an idea of something like weight, height, something that's I can do an X bar to, that you think today is smaller than it used to be in the past? I can think of a lot of percentage questions, but I'm just having a hard time getting my brain around a particular made-up story where something in the past was bigger and today it's now smaller, or at least we think it might be.
The weight of computers. Good
one. Okay. In 1980, when personal computers kind of maybe came on the scene, right? In 1980, an average computer, and I'm making this up, weighed 20 pounds, right? Whatever it really was. Okay.
Well, I have one from 1981 that weighs 45. So there's that for you.
Weighs 40 pounds, right?
Yeah, yeah.
That'll work. So in 1980, the average computer weighed 40 pounds. And someone wants to put together a very short article on the changes to, excuse me, the changes to computer weight. So he believes that today, oh, first I'll have to put a sigma. Can we put in a sigma of 15? Just because I feel like it. And they believe that today that computers are much lighter. So the null hypothesis would be that they're still 40 pounds. And the alternate hypothesis is that they are less. And we want to test this thing at a significance level of 5%, right? So we're willing to do this process and get it wrong 5% of the time. Now, the reason why you need the significance level, I know you need it in the p-value, but the main reason why you need it is that nothing in statistics that you ever do is really 100% guaranteed. All we can do is qualify it with a number on to indicate how confident, for want of a better word, you should be in this result. So if I'm willing to be wrong 5% of the time, does it not mean that this particular one might come up with a conclusion that is wrong? In fact, it probably will, these kind of stories, 5% of the time. Or 10% of the time, right? That's another significance level. Or 1% of the time. But no matter what it is, it's still going to be wrong, or a chance that it is wrong 1% of the time. And that means that because of this process, do you know that any scientific paper that's written that uses this, even if it uses a significance level of 1%, isn't 1 in 100 of them telling us something that wasn't true? Right? If there's only one paper on it. Now, thank goodness that doesn't happen, because what happens if somebody finds something really interesting? Doesn't the University of Paris say, we're going to check that out and do our own survey and our own hypothesis test? And gone darn it, we came up with the same evidence that you did. Now, isn't it much harder to be wrong twice when it's a 1% chance of failure, right? It now becomes a 10,000th, right? A 1% of 1% chance. And if 3 places in the world do it, it's a 1,000,000 to 1 chance. And at that point, people just say, yep, you're right, whatever the result was. So, set up. What do you think this one's going to be called? If that's called a right tail test, what do you think this one's going to be called?
A left tail test.
Sometimes the obvious is the answer. I believe there's some homework questions where they mention left and right, so now you know where it's coming from. I don't know if they call it tailed, they could say it left interval test. Right, that's another one. Right, so step 2 then. Step 2, collect the data. Put a little line there. What do we know in step 2? Well, you go out and you collect a sample. And this time, he's feeling comfortable, so he only asks 10 people. And he gets the answer, £20. And he's good to go. Well, almost good to go. Don't we now find the standard error? Which in this case is 15 divided by the square root of 10. Oh, by the way, I'm making an assumption here, which I should have told you. I'm making the assumption that the weights of computers are nice and normally distributed, right? So it's a single mound. I think it's reasonable, but I'm still making that assumption. 15 divided by the square root of 10. And I am looking at about 4.74. And so all of that was so that we could find the z-score. You can just call it Z if you like. I did the last time, but its full name's a z-score. And the z-score is made up of sample, take away mu naught, divided by the standard error. The sample in this case was £20. Mu naught, right, that guy there, mu naught is 40. And the standard error is 4.75. So we have negative 20 divided by 4.75. And this time the z-score is about negative 4.21. Okay, gut feeling. Do you think this one's going to be statistically significant? We still have to go through the process, but just looking at it, does it look statistically significant? Is that z-score unusual in size? Yeah. So what is unusual? Do you know 3 are bigger and negative 3 and less? They're unusual. And do you know in some circumstances, the high 2 points can also come up. So see if you got a 2.8 or a negative 2.8, they can sometimes just sneak in as statistically significant as well. So step 3 is calculate the p-value. So it's going to be the probability that we get a z-score less than negative 4.21. Now, I'll just put this guy beside it. You notice that the major difference here? Oops, somebody's went again. Can you see the major difference here is greater than 8.7 in the first story and less than negative 4.21. Can you see why that's called a right tail test? You're getting this guy? Can you see this guy's going to be way over on the left? I mean, if I drew a little picture of him, he would look something like this. Right? A left tail test. Well, let's figure out who he is. Well, we know it's a normal CDF, so I'll put that in. Now, if you want to be less than this fella, you put in negative 999. You then put the negative 4.21 guy, a mean of 0 and a standard deviation of 1. Here we go. And so second distribution, the second choice, normal CDF, negative 999, comma, negative 4.21, comma, 0, comma, 1. Close the thing off, hit the enter. And I get 1.28 times 10 to the negative 5. I think that one just sneaks in as doable. You see, I can just about write that down as a decimal without being silly. Really tiny, agreed? The chances that what we saw happening by sheer chance is like, it's close to 1 in 100,000. Not really likely. And that's good, because what that means is stage 4 conclusion. So I'm going to put stage 4 here. In the conclusion, it's always, is the p-value less than alpha? It doesn't matter whether you're trying to prove a right-tailed test or a left-tailed test or any other tailed test that you can think of. The conclusion is always based on the answer to this question. And in this case is 0.123400128. Is it less than the alpha, which I chose was 5%? And again, the answer is yes. So we can really go to town here and finish off with a very special sentence. Bending all sorts of bits of paper here. I'll push this maybe a little bit up. Isn't it a statistically significant result? So we have enough evidence to reject H0, and so HA is true. In other words, computers in the past, computers today, let's phrase it that way, computers today are lighter than they were in the past. Because this p-value is so tiny, couldn't we say to ourselves, we are really happy that this evidence is very strong. Such a tiny number is probably never going to happen by sheer chance. So we could say, not that you can strengthen that, but I guess if I was trying to, we can say that there's statistically a very significant result, but you don't, right? You just say significant and that's good. Now, there are 3, although I'm not going to do the 3rd version just for time purposes, because I still have the other story to do. But there are essentially 3 versions of number 1. The first one was the null hypothesis, mu equals 63, and the alternate was that Scottish people are bigger. There was that the mean was 40, and the alternate is that it's less than 40. And the 3rd one, which we haven't done, so I'm just going to make up one, that the average age of Americans in the past was 32, and the alternate is that today it's different. This fella is a right-tailed test. This fella is a left-tailed test. This guy is called a two-tailed test. So when you get one of your homework questions and there's a hypothesis test there, one of those little, you know, the 4 choices, the little circle things, one of them's going to be it's a right-tailed, one's going to be it's a left-tailed, one's going to be it's a two-tailed, and I haven't a clue what the 4th one is, but there's probably a 4th one. And you'll just dot it on the right one. Do we feel comfortable about this hypothesis testing process? You feel you got it. It's very mechanical and it's very lawyer-esque, which is a made-up name, but it's very like a lawyer got here. You got to do it this way. And the reason why they're so strict about you got to follow these lines is so that if everyone follows these lines, and we all will then agree on the conclusion at the end. But if you start fudging it and and tweaking it and doing stuff that's not the same as other people, do you see that just introduces the opportunity to argue about the conclusions? But this is a tried and tested method. It's still done today, probably will be done forever, on how to go about proving that you've got evidence that something is true, right? Proving that something has increased, proving that something has decreased, proving that something is not the same as it used to be. We good? Right. So our next group of stories, I wish I hadn't written on that now. Is that we're going to do stories with percentages, proportions, hypothesis tests, with proportions. Yeah, with percentages. So here's my first story. In the past, the percentage of people who were in favor of capital punishment, right, people being hanged for serious crimes, was 51%. Right? Now, in the past could mean 10 years ago, it could mean 100 years ago, whatever it is, right? That's in the past. We are going to, a social scientist, probably, thinks that people's opinion today has changed. Right? And he thinks that less people are in favor of, hanging someone or whatever, lethal injection, whatever method it is. Less people today than that number, right? So we're going to go and set up a hypothesis test. Let's have a significance level of 1%. You've got to have something. Now, by the way, if this book comes up with some weird alpha, I'm going to swear, right? So you're all going to put it on mute so you can't hear me. I've seen enough 80% confidence intervals from this book to drive me crazy. And I was looking through something, and I believe one of them was a 93% confidence level. Did you see one where it was some weird number that wasn't even 90 or 95? It's like the computer. Maybe, now I'm thinking about that, maybe I shouldn't be so hard on the guy. I think it might be the computer is just randomly picking confidence numbers, right? 90, 95, 93, 97, 80, like picking them out of a hat. So maybe it's not his fault. Right, let's be generous, maybe it's not his fault. But they better not make that anything else except 1, 5, and 10, right? Because I just refuse. I'll if you see one, tell me, I'll take the question out, right? I'll just destroy it. I don't even want you to attempt that in case it brings bad habits, right? In case you start thinking, well, he could do it, I can do it, right? We're not going to do that. So what did he do? Well, this guy goes out there and he gets some money, as you do. And let's see what he has. Well, the null hypothesis and the alternate hypothesis has to be set up. The null is that it was 51, and the alternate is that it's less than 51. Do you see that's almost the same thing you do with means? There is a difference. Wasn't that called mu, the population mean? Now it's called P, the population proportion. So he goes out, and that's step 1 done. And he collects his data. And he collected 300 people. Simple random sample. And he came up with the answer that 157 of them were in favor. Oops, I don't want 157. I want the other side, because that would be definitely bad evidence. So 150. So 147. How about that? That's better. So let's see what he got. 147 divided by 300. And he found out that, oh, that's a nice number, actually. I didn't realize it was going to be so bright. 49%. Superficially, wouldn't you think that would be quite good evidence? 49% today. It used to be 10 years ago, 51%. It's definitely reduced. Well, the reason you cannot do that, that would be anecdotal evidence, is if you took a sample of 300 people, again, a different sample, couldn't the next time it be 52% said yes? And then you take another group and it's 47%, and another group and it's 49 again. Because when you take samples, don't you just get random combinations, and sometimes they're a little bit big and sometimes they're a little bit small. What we expect is in the long run that they kind of average out. So there's no guarantee that that's evidence yet. Gut feeling, does it look like it might be? Do you think a 2% difference is going to cut it on a 1% significance level? You got a gut feeling on this one? Still a bit early? Hard to tell? See, when I get to the Z-score, you better have more than a gut feeling, right? Because you should be able to tell when you see a Z-score, right? A Z-score of 14, you're in trouble, right? That's really weird, right? That's going to be evidence. A Z-score of 0.9 ain't going to happen, right? That's just pretty normal kind of Z-score. Now, we have some other guys to get. We've got a guy called the standard error to get, and of course the guy called the Z-score to get. And they're going to have very similar formula here. This guy is going to be P hat, take away P naught over the standard error. Is 51 or 49 the P naught, based on what happened in the other question? Is 51% or is it 49% is going to be the P naught? It's not a trick question. This one? Great. It's kind of giveaway. It's called P hat, right? So I know, oops, changing pens. I know that I've got 49. I'm going to take away 51. Now, standard error. That's a bit of a different equation. When it was means, wasn't the standard error for the population, the sampling distribution, sigma over rho n? Can you remember what it was when it was proportions? It was P naught, 1 minus P naught over n. Do you notice that you use this number and not that one? See what I did there? I used this number, not that one. Now we put this fella in, a little here. It's going to be, oh darn it in space. By sheer coincidence, isn't 1 minus this guy that number? Pretend that's not true, right? It's always this guy take away the rest. So I'm now going to do that guy in my calculator. Hopefully I can get it in one go. It's going to be the square root of 51 times 49 divided by 300. And the answer I have is 0.0, oh, let's just call it 3. I want to make my calculations easy to do. It's 0.0288 or something, right? So that means in here it's going to go 0.03. And that comes out, let's see what that comes out to be, 0.49, take away 0.51, and then I'm going to divide that by 0.03, and I now have negative 0.667. Okay, gut feeling time. Do you think that Z-score is going to get me a statistically significant result? Nope, agreed. Ain't going to happen. Shouldn't that guy be big? Big in negative or big in positive? Depends on the story. Shouldn't that guy be 4.8, 17.1, or negative 3.2, negative 5.9? Those are the kind of numbers that are going to get me statistically significant results. That guy is going to get me a not statistically significant result. But we still have to go through the process. So here goes. Well, that's step 3 done. Step 2 done. Step 3. Let's get the p-value. It's the probability that you get a z-score. A z-score bigger than this or a z-score less than that? Which is this going to be? A z-score bigger than this decimal or a z-score less than this decimal? Any commit? You see this guy up here? Follow him when you're not sure. Whatever the alternate is pointing at, point the same way. Now, I'm going to go in and do the normal CDF here. A less than is going to get me negative 999, and negative 0.667, a 0 and a 1. See what that looks like. Negative 999, comma, negative 0.667, comma, 0, comma, 1. 0.252. What that is telling me is that in this question here, in this story here, the chances that you got, the result that you got from your sample would happen about 25% of the time just by sheer chance. So there's no evidence to say that's unusual. This is exactly the kind of thing you may expect to see, right? A little bit of variation because it happens. So conclusion. This is not statistically significant result. We can just write down there is not enough evidence to reject. It's not. Does this hypothesis test that we've just completed, does this mean then that we've proven that 51% of people are still in favour of capital punishment today, just like it was in the past? Have we proved that that's the same?
It's inconclusive.
It's exactly that. We haven't proved essentially anything. In fact, couldn't we have spent $10,000 and at the end of that $10,000, we're no better off than we were before we started? Can you see why there is a very strong motivation to get statistically significant results? Because if they're not statistically significant, no one ever writes a paper and sends it in for peer review in which they say, let's pick and poor Olivia. We've just dug up some bones, and I can tell you for sure that we haven't been able to prove that these people's bones are more than 200 years old. People are going to say, you haven't really proved much then, have you? In fact, you haven't really proved anything.
That sounds like archaeology to me. All we do is ask for money.
Oh, and then you do it, and hopefully you get some stuff. I think, I'm hoping, and I think it might be true as well, that as you go through this process, as weird as it look, there's at least, it has a flow to it. There's a step 1, a step 2, a step 3, a step 4. There's a story at the end where all the numbers that you need to get are there. Right? You just take them and you go with them, and you pop out at the end. And when you pop out at the end, it's either statistically significant, or as in this case, it's not statistically significant. Which the analogy would be, you convict a guy and he's now in jail, or you let him go free. This would be you let him go free situation, right? That would be the analogy. Of course, when you let someone go free, does it mean they're innocent? Did they commit the crime, even although you let them go free? No, is the short answer. Aren't there some guilty people who walk free every day? They commit the crime, but there just wasn't enough evidence to convict them. Aren't there some people in jail today who didn't commit the crime? Those are the ones that we said it was statistically significant at, say, the 1% level. And we got data that proved, we got evidence, his blood group or whatever it was, right? He was in the same place at the same time, whatever the thing is, if you could put a percentage on. We got all that together and we convicted them on what is essentially circumstantial evidence. And he's now in jail. Now, what you would hope that in a good legal system, wouldn't you hope that maybe only 1 in 1,000 people are wrongly convicted? Actually, I prefer it was 1 in 1,000,000, but you got to be realistic. If I made it so that only 1 in 1,000,000 innocent people went to jail, right? So if I made the poll so high, wouldn't there be an awful lot of guilty people walking out of jail every single day? And so there are what's I'm trying to get to here? The legal system has a contradiction going on in its brain. One side of it is we have to protect people from bad people. We have to protect people from others who will come and steal your stuff, or beat you up, or rape you, or God forbid, kill you. Right? We've got to protect ourselves from people who will do that. So if they commit a crime, you want them to be in jail, because if they're in jail, they can't do it anymore, right? But at the other side, you don't want innocent people going to jail, because that's just a terrible thing to do to an innocent person. But there is no way in the world that you're going to get 100% success. See, if I wanted to make sure that every person who was a criminal was sent to jail, wouldn't there be a lot of innocent people end up in jail because of that? So don't you have to do a kind of balancing act by how many people who are probably guilty, but you're willing to let them go to save some innocent people from going to jail? And you can tell a country's, I don't know if it's morals, but you can tell a country's issue to criminal reform based on how they treat the people in their criminal system. For instance, don't go to France and get arrested for major crimes. Do you know a lot of what's the word? They use a 3-judge system. So in other words, there aren't 12 people, right, to hear your case. Just normal people off the street, right? Normal Americans. They pick 3 judges, and the judges vote based on the evidence. And if it's 2 judges say you're guilty and 1 says you're innocent, you end up in jail. I don't think that system would work well. Now, thankfully in France, you can opt for a jury. So if you get charged with a crime, you can say, I'm going to go for a jury. And I believe, and it seems back to front, but do you know if if you've been charged with murder? A lot of people on the side of they probably did it go with 3 judges. And I think they do it because their brain works and the experience has told them that judges don't really care so much about the evidence, but the process. And so all you need to do is get a couple of, they never done this right, they never quite followed the way through procedure. And that's enough to get a judge to say, I don't feel comfortable now about convicting this guy. Anyway, the good news is that none of you are ever going to murder anyone, right? Or be murdered. And you're all safe. And that is good. So I think we should do one more percentage one. And then that would be a good, let's have a break. Right? And then when we come back, I'm going to show you how to do all of this using the calculator. I thought I'd get a better reaction than that. I thought I would get, you mean we've suffered this? Oh, that's good. The reason, after I do this last one and we come back, the reason why I had to do this the long way, right? You know, every step, was so that when we come to do it in the calculator, which will take most of the grind of the number crunching off your hands, you should be able to say, I know where these numbers came from. I know what they did to get that. This isn't him just saying press some buttons and read off a number at the end and you're good. So I think you have to suffer the process to understand the process. But once you've suffered enough, won't you start grabbing a calculator and do it the faster, efficient way? So I can move on then. The analogy is, I know how to multiply two-digit numbers by four-digit numbers, but once I've figured out how to do that by hand, doesn't every human being use a calculator? So statisticians do the exact same thing. A person who does this for a living will not do what we just did by hand, right? They will do the process the way I said it, but they will do the number crunching using the features. So I think we should try and use ULOT. So it's a very small sample, 2, 4, 6, 8, 10, 12, 14, 16, 18. And I need a story. Okay. Let's say we asked 5 months ago what percentage of people had left the state, had went from one state to the other, right? How many people have done that? And the answer that we came up with was, in the past, making this up, 20% of Americans had went to another state, right? So in the last year or whatever, no, it can't be the last year, in the last 5 months, right? I went to another state. And because of the COVID, we believe that that number is now a lot smaller, right? That people haven't been to another state. Not saying that you couldn't have, because some of you may have, hopefully some of you will have, but right now it looks unlikely. Now I want a significance level, so I'm going to go for a 1%. And so my H0 is going to be that it's still what it was. It's 20%. And my alternate is that I believe is much less. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's step one. Step two then, we're going to collect our data. We have 18. And I may cheat on this depending on the results I've got. So for the 18 people, that's you lot, how many have actually in the last 8 months been to a different state? Shooting space. 1, 2, 3, 4, 5, 6. Okay. I believe that has now increased. I think we got, the last number I stopped looking at was 5 out of 18. Oh, I know what to do. This is better. Let's do a two-tailed test. We believe it's different. See, that kind of, I should have probably picked that one, right? Just to be safe. And so our p hat, 5 out of 18. I didn't realize Is that because I chose too big a time period than it was before COVID? Too late now. I probably should have said how many in the last 2 months, but we're not changing the story now. So we've got 5 divided by 18, and that ends up being about 28. Let's just make numbers nice. Okay, so 28%. Interesting. What do we need? We need a standard error. It's the square root of P naught, 1 take away P naught over 18. And that's going to be a 0.2 times a 0.8 over 18. So I'm doing a square root of this guy, and a 0.2 times a 0.8 divided by 18. I've got a 0.0, I'm doing pretty crude rounding off here, 0.09. And so my z-score, p hat, take away p naught over the standard error, is 28 take away 20 divided by 0.09. And that comes out to be 0.08 divided by 0.09. And the answer I got was 0.89. Okay, gut feeling, does that look like it's going to be statistically significant? A z-score of 0.89, does that look statistically significant? Nah, right? So to finish the question, here goes. I'm going to get a p-value. It's a probability. Well, now that I know that this number is positive, won't I be looking for that number or bigger? Because this is a two-tailed test. So it could be over here, or it could be over there. The one we got was over here. So in our distribution, number 2, 0.89 or bigger, mean of 0, standard deviation of 1. I am looking at a 0.19. And so, conclusion time. Is our p-value less than our alpha? Is that less than this guy? And the answer is no. So this is not statistically significant. So we can write down there is not enough evidence to reject H naught. Okay, before we have our break here, let's look at this story. Firstly, I probably should have just said not equal to, especially when I didn't know what you lot were going to say, but we fixed that. What do you think is the main reason why we didn't get any statistically significant result here? Right, from a practical perspective,
The sample size is too small.
That's it. Would you agree, asking 18 people, it's really hard to get any statistical significant evidence? Technically speaking, this one works because the book has NP bigger than 5. In other words, did 5 people say yes to this question? The answer is yes. So theoretically speaking, it was okay to do it. It really would probably need, and I'm guesstimating here, but we would have needed maybe 10 out of 18 of you to say yes, right here, before it would be big enough here, right? Before this would, I should say, a big z-score would lead to that being small. And that is us. Are we good? So I'll give you a 10-minute break, which means I'll see you back here at 25 past, and I will be getting set up for how to use a calculator to do very similar results. Right? I gotcha. Okay, come on, let's go. Oh, like scum? Olivia, you went and said you can estimate the height of a person by just measuring one of their long bones, correct?
You can, yeah. It's an estimate at best. You
Uh-huh.
kind of have to know a lot about certain regional differences in the way people are constructed. So it also helps to have a tooth in addition to it, because the scale of teeth, you can also estimate the general size of a person. But for kind of a ballpark range, yeah, you can use any one of the long bones.
That is interesting because chapter 9 does linear regression. And linear regression is almost certainly how that estimate came up. Because on the x-axis, you would have length of long bone, and then on the vertical axis, you would have the height of that person. So all you need to do is collect good data that you know the height of a person, because you have the whole skeleton, say. And then you take that long bone and you measure it, and it's typically, hopefully, quite linear. And that's how that came about. So you will actually see something like that.
Yeah.
I don't have the real data, but I'll just make up data similar to what they might have.
Yeah, it's at the site last year, we had, gosh, what was it, 3 10th century burials that we pulled up, and they were in terrible condition. So we only ended up with about half of each skeleton, and we didn't look at any numbers. It's a lot of guessing and speculating, and until we can actually get some decent money and did run labs on a lot of these, it's a lot of guessing. But we were hoping to get some labs done this year. We were going to do some carbon-14 testing
Okay.
on several of our samples, but COVID has shut down the entirety of Bulgaria. So
Oh, that's it.
maybe next year.
So in Bulgaria, what is it you're studying? Are you just studying the people through history who lived there, or you got a theme?
No, actually, I'm on a site right now that's a military station. We think it is. We haven't found a definitive inscription anywhere, which is kind of the holy grail. I mean, a treasure is great, but an inscription would be even better.
So you want a piece of stone carved in ancient Bulgarian, if there is such a language, that said, "This is post number 4 to defend river in name of
yeah, we
whoever emperor it
dates.
was."
Oh, it'd be great. But we actually found a couple of inscriptions last year, but they aren't of the same age range of the site. There's actually a Greek site, an ancient Greek site down the road a ways, where they had, it was like a trade post or something, and so the Romans came and poached the stones from this building and used it to build their military station, just to confuse us, I'm sure.
Yeah. Well, if you go to Rome, you'll find some of the churches are built with stones that were buildings that were Greek temples or Roman temples and all sorts of things. Blocks of stone are, they were a bit cheapskate in those days, so I knocked that thing down. It's half fallen down anyway. Use all the good stones, and some of them, you have people's houses where, if you look really carefully, you'll find pieces of archways in their house. They just went and stole a piece of stone from a ruin and, built their house with it, or at least with part of it.
Yeah, well, the funny thing about my site is that we're only just starting to get to the Roman layers of occupation, and where we're at right now is around the 10th century, where there was a lot of peasants who moved into the fortification and built their little houses out of the rubble that had fallen down from the Roman sites. Because why would you go and build a new house when you've got a perfectly good wall here, and that's a good part of your building done already?
Yeah. And so what do you think you're going to get to the Romans? What did the Romans call Bulgaria? Did they have a name for it? Don't tell me it's Bulgaria or something really boring.
No, it was Thrace. It was Bulgaria, Proto-Bulgaria, I guess, once the Ottomans moved in around the 10th century and onward. But Thrace is what that region was back then.
Thrace? Ah,
Mhm.
okay. Yeah. Useless piece of information. When I was at university doing my master's degree, I shared an office with a Greek student. And I don't know if you know anything about Greece's history, but um, there was a time in Greece when it was ruled by what was called the generals. It was basically a dictatorship. And so most of the people who were like the governors of districts were military. So it was all, top-down military and very few civilians. And anyway, his dad was a chief of police. And I was just thinking, he would have been a good friend to have if I ever went to Greece. But they changed. Thankfully, they changed their politics and they became a true democracy.
It seems like they're doing better ththese days as well. So one of my colleagues down in Bulgaria, he visits quite often, and after they got Macedonia under their thumb, or what do they call it now? The Republic of North Macedonia. Once they've got that whole territory issue sorted out, I think there's a lot more stability for them in their future.
Yeah, so I think, the Macedonians with Alexander the Great and all that vibe going on. I don't think the Greeks like that name.
Oh, no, they do not.
So there's a little bit of contention because of that. I'm not even sure if ethnically are the Bulgarians Greeks.
Oh, no, they're Bulgarian, if you ask them.
Right, but I mean,
Oh,
racially, if you did a DNA, would Greeks and Bulgarians like share 80% of the same genes?
probably, but don't say it too loud.
Oh,
So they're both going to have a problem with that. But yeah.
is that like calling me English?
Yes, yeah, exactly.
Okay, I got it. Yeah, gotcha. So what, Bulgaria is still a democracy? It's not one of those pseudo-democracies where they have basically an ex-KGB guy in charge. He just pretends he's a civilian. Is it a real democracy?
Kind of yes and no. They're heading towards better democracies. The biggest problems right now are just skimming, and it's actually kind of reined in a little bit these days. They're doing better.
What did you call that word? Skimming?
Yeah, skimming off the top, like
Oh,
embezzling.
corruption.
Corruption, yeah.
Okay, I gotcha.
It's not as organized these days, though. It's actually most of the corruption is happening in the small local governments. So, while not ideal, it's a decent change, I think.
Okay, it's better than the past. So
Yeah.
you're talking about the kind of thing with Tatum is if a road had to get retarmacked, the mayor would make sure it was his son or his son-in-law or somebody who gave him $5,000 would get the contract, regardless of how well he did the job and
Precisely.
regardless of how much he charged for doing the job.
Yeah.
That kind of-
Yeah.
yeah.
And the problem we're having right now is that Bulgaria is getting a ton of money from the EU for.
Ooh, not a good idea to give corrupt countries lots of money. It just isn't.
Oh no, they're getting so much of it, and they were named. Oh, what was it? Like the center of culture, the capital of culture for Europe for last year. And so as a part of that deal, they got tons and tons and tons of money to restore like a big Roman amphitheater and all sorts of other ruins, hoping that it would drive tourism because after the Soviets moved out,
There weren't a lot happening.
No, not at all.
Gotcha.
And tons of that money got stolen. And so there's big investigations going on right now. And all the archaeologists are really
call me
embarrassed.
naive, but the EEC people who were handing this money out, it never crossed their mind that that might happen to that money.
Yeah, they're the Bulgarians of all people. I don't want to know how much. It's a really high number, like percentage-wise, that got skimmed.
Like 50% of it never made it to whatever it was meant to go to.
Oh no, nobody has any idea what happened to it.
It just disappears.
No,
The Italians,
nobody saw this
the
coming.
Italians are sometimes like that. It's not big government, but it's if you go to towns and so on, there's a fair amount of nepotism, if that's a better word,
Yeah.
where contracts are given to family members and money just sort of disappears.
Yeah. So I went through Tuscany last year on the way home, and that was really nice, but it's very obvious that there's a lot of these political issues going on in small towns because they look terrible. And despite all of these initiatives, they're offering people tens of thousands of dollars to
Oh
move
yeah.
to the countryside and open businesses, and
You can go
people are
to
taking
Naples.
up on it.
You can go to Naples. We were in Naples on our way to Pompeii. So we went and we drove through Naples, and there's buildings in Naples that are still damaged from the Second World War that they haven't got around to repairing yet.
Jeez, are you serious?
Mm-hmm.
Oh, checks out.
So
I love it there, though. It's have you been
I
to,
love Italy. Yeah,
yeah.
I wouldn't give the politicians a penny, but I love Italy.
You know, I was thinking about like getting land out there to have an olive grove because I'm thinking like, oh, that's got to be lucrative. You know, olive oil costs a ton of money, and I was pricing it out, and I think just to break even, you need to have 3,000 trees, and yeah, it's mostly your money goes to taxes. I mean, the properties out there are cheap, but the property taxes out there are insane. They're ridiculous.
Well, I don't know how we'll have to get moving here. So that was fun. But let's go and have a look at, and I'm trying to find out which guy we've got. This one here. I promised you, and trust me, I will do it. But before we do that, I want, okay, that's fine. Let's have a look at our first set of homework questions. And I want to go over some of the stuff from 8.1. And then once we get to, I think it's about halfway, I'll start showing you the calculator stuff, right? So what is a null hypothesis? And there, this is the answer. A working hypothesis making a claim about the population parameter in question. I wish they'd put that in better English, but you can see I'm giving you the answer, so you can figure that out yourself. If you pause this video, you can go back to these and find out what the choices are. The alternate hypothesis, they're calling H1. I refuse to call it H1, it's HA. And what's that? That's anything that differs from the original. And this is something I didn't cover. Type 1 error is rejecting the null hypothesis when it's true. Do you know the significance level alpha? That is type 1 error. That's what it's called. And type 2 error is failing to reject the null hypothesis when you should have, and that's called beta. So, oh, there it is there. Type 2 error is beta. And alpha is type 1 error. Here is left-tailed, right-tailed, and two-tailed. And how do you tell which kind of tail it is? Don't you look at the alternate hypothesis? If it says mu greater than 10, it's right-tailed. If it says mu less than 10, it's left-tailed. And if it says mu doesn't equal 10, it's two-tailed. And I just put 10 in as an example of a number. We've already talked about that too. And here we have some stories with the alternate or the null given to us. So the first one is question 5. Suppose we want to test a claim that a population mean equals 40. You would do that guy there. H naught, let's kind of carve this in stone. The null hypothesis H naught is always going to be mu equals a number or P equals a number. It's not going to be anything else. It's never going to be less than or greater than. It's always equal. And the number that it's equal to depends on the story. So when you read the story, very often at the beginning, they tell you what it was like previously in the past. And that's the number you're going to use. Mu equals 63 inches. That's what Scotsman used to, height used to be in the past. Mu equals 20, P equals 20%. That's the number of people who had been out of the state in the previous year. And here's some various alternates, and they even have some stories here. And here's another bunch, same idea. And here's another bunch. So hopefully by the time you're really good at pausing quickly, you'll be able to do these guys. And here we've hit our first question. And that's where I'm going to stop, because I'm now going to show you how we can do the same basic question but we're going to let the calculator do it for us. Okay. Now, where am I going to put this guy? Okay, let's stop sharing. Okay, what's going on? You guys have disappeared for a second. Are you there? Somebody talk to me. Oh, good, you're there. Whew. Been having weird computer issues lately. Okay, I think I'll probably just use this calculator on that one. It means I can do everything at once. So I'm going to do a story, very similar to the ones we've done, but now I'm going to show you how the calculator can do pretty much everything for you. Do you want a main story, a thing with an X bar in it, or do you want a P story, a thing with a percentage in it? I'm just going to make up a story on one of those two. Have you got a preference? We'll do an X bar story. Okay, Chloe, what were you going to choose for us at that?
I just said, can we do a percentage?
Okay, we can. So let's suppose that in the past, the percentage of people who, the percentage of married people was 65%. And a social scientist thinks that that percentage is now less, right? Fewer people actually get married, right? Doesn't mean that they don't have a stable relationship, they just didn't spend a lot of money. Actually, it doesn't cost a lot of money. So if you've got a partner and you want, don't shake your head, if you've got a partner, tell them Vegas do really good deals. You can go down there and get married and have fun at the same time. It's a bit like going to Vegas and kind of you get married kind of as a side issue. Right? Me and my wife, well, I have this plan, she doesn't. When we meet, I don't know what the next big one's going to be. Next big one, when we get to 30 years married, maybe 40. I'll wait till I'm 40 years married. I want to go down to Vegas and get that thingy, your vow thing, and I want to get married by Elvis. That you would do, Zoe. You would get married by Elvis. Okay, so we share that. So, and
My husband and I eloped. It was great.
Oh, that's cool. Did you
Recommend it.
Did you go to Vegas and get Elvis? Because that would make me really jealous.
We didn't. I wish we had. I do, but no, we didn't.
Yeah, but when you get round to the next round number, you might
We'll do it. Yeah.
do a little thing, right? My wife's answer to that is, well, you're going to get married on your own. So I don't think that's probably going to work. Anyway, back to this story. 65% of people get married. This social scientist thinks it's better. Better is worse, right? It's got less. So H naught, the null hypothesis is at 65%. The alternate is that it has went down, right? We're going to do a significance level. Anybody got a preference? It's just part of the question. Say 5%, as good as any. And we are now, that's stage one done. We're now going to have some data. This data, for the most part, you'll get, right? So can we tell you that P hat is 57 people out of 100, right? So basically, they did a small sample of 100 people and 57% of them were married, right? Now, clear this out the way. We need to go hunting for where this guy is. Now, I know you don't know where it is, but you get any guesses where it might be? Stats? Have you any idea where they might put a hypothesis test?
Test.
Have you noticed that this last menu is very busy? There is a lot of stuff going on here. And we are looking for proportions, and it's a one proportion test, right? So I'm going to scroll down to choice number 5. And I'm going to hit enter. Now, do you see that they ask us to put in certain information? And let's see, it's quite cryptic, but the first thing they want us to do is put in P naught. And can I tell you that that guy is 0.57? Are you quite happy where I got it, right? 0.57. So 0.57, enter. X, by the way, that's called X and that's called N, right? Just in case you're wondering. Actually, that's sometimes called R as well, go figure. This is 57 out of 100. Okay, so do you see, basically, don't you just tell people how many said yes in your sample, 57 out of 100? I think it's a little bit out because I just said the wrong fella up here and nobody corrected me. That's P naught, isn't it? And shouldn't P naught, and I'll put a little arrow because maybe I'll remember it, isn't that guy P naught? There, now it makes sense, right? P naught is 65. 57 people out of 100 said my thing. Now, which one of these is the guy that we're going hunting for? Well, aren't we looking for a less than fella? Right? So P naught, right, with a less than. Agreed? I mean, that's kind of the way they label it. And now I'm going to go down to calculate, and let's see what we get. You get a z-score. You get a p-value. That p is really your p-value. It's rather distracting because doesn't it look like you were telling me this guy, or you might be telling me this guy. But p-hat, which we already knew, was 0.57. And they tell us 100. Those two are probably not that useful because we already knew them. But would you agree these two guys are very useful? In particular, isn't the most important guy to know is the p-value. So don't we basically jump straight to step 3? It will tell me the p-value for every percentage story, right? You just plug in a few numbers and it will tell you the p-value. So conclusion time. Is our p-value less than alpha? In this case, is our 0.047 less than 0.05? And I know it sneaked in by a whisker, but didn't it sneak in? And so the answer is yes. And now I'm going to get lazy. I'm not going to say it, but can you imagine where all these dots are? I would write the following. This is a statistically significant result. There is enough evidence to reject H naught, and so HA is true, right? The jargon sentence at the end of this. Haven't we proved then that today less people are married than in the past? That would be the kind of social science paper, right? We've got evidence, statistically significant evidence, to prove that fewer people are married today than were in the past. Now, have you noticed that that cut out a whole chunk of you don't need to calculate standard error, you don't need to calculate z-score, and you don't need to calculate the normal CDF? Do you see that big chunk in the middle has now been done for us? There's your z-score, and there's your p-value. Much cleaner, much nicer. Now, you still have to do a bit at the end. Don't you have to make your conclusion up based on the p-value? And don't you have to do a bit at the start where you write down what the hypotheses are? But I would say it's half the work, at least, if not more. Agreed? Now, I'm now going to do a story with X bar, but it's going to be a little bit different. In the past, the average weight of a chicken was 4 pounds. I'm not sure who would do this job, an agriculturist, has decided that he thinks the chickens of today are bigger and heavier than the chickens of the past. And he wants to prove it with a significance level of 0.1. And so what he does is that he gets a small sample and he gets the following guys. Let's say he gets 7 chickens, no particular reason why it's 7. And the chickens weigh 3.9 pounds, 4.2, 4.5, 5.1, and 3.8. Now, when you look at that, those, I need 2 more, don't I? 4.1 and 4.7, right? 1, 2, 3, 4, 5, 6, 7. Right, when you look at these 7 guys, right, is there enough evidence based on this small sample size that chickens are heavier? So let's do the process. The null hypothesis is that it's what it was in the past, 4 pounds. The alternate hypothesis is that chickens of today are heavier. Now we're going to take that information and we're going to put it into our calculator. And I'm going to hit start and I'm going to go over to tests. And then I'm going to be looking. Well, I guess the question is, who am I going to go looking for? Do you know which one I'm going to pick? It's on that window. It's a Z-test or it's a T-test. Have you noticed that I am not told sigma here? Remember when you were doing confidence intervals and you weren't told sigma, didn't you have to do a T guy? So that's why I'm choosing choice number 2. Can we pretend that this question was the same question with 1 extra bit? Somehow or other, we told you sigma. Right? Can you imagine they might have done the question, but they told me sigma. If they had told me sigma, do you know I'll use number 1? Number 1, sigma known. Number 2, sigma unknown. Can you remember doing intervals? If sigma is known, didn't you do a Z interval? When sigma was unknown, didn't you do a T interval, right? It's the same idea. So back to this guy, T-test, boom. And of course, I've forgotten something. Don't I have data? Doesn't the data need to go into my calculator? So I'm going to hit start, I'm going to go into edit, and I'm going to clear out all this data, and I'm going to put in all these guys. So 3.9, 4.2, 4.5, 5.1, 3.8, 4.1, and 4.7. Okay, then I'll go back again. Start, tests, number 2, T-test. I guess I'll put that up here. Number 2, T-test, right? Okay, let's see what we have here. Isn't that guy knew not? So I'm going to scroll over and I'm going to do data, because this question is based on a set of data. And now I'm going to go knew not, 4 pound chicken. Would you agree that the data is stored in L1 and the frequency is 1, so we just zoom by those. In this story, don't I want the bigger than? That's that choice. And then I go to calculate, and let's see what we get out of this. The most important guy is the p-value. Which is what, 0.055 roughly? That's basically, isn't that step 3 and step 2 done for you, even if I don't write it down? So I now go on to our last step, our conclusion. Is our p-value less than significance level alpha? Is 0.055 less than 0.10? And the answer is this less? Is this less than that? It's not meant to be a trick question. Is this less than that? If I cover up the 5, does it help?
Do
Talk
we
to me.
want
So,
more than?
no. P-value is always less than alpha. It's always less. No matter what this says, this could say less than 4, greater than 4, not equal to 4. The test is always, is your p-value very small? Is your p-value less than alpha? Always that. So that was a good comment because it'll get me to emphasize that. So this is definitely less than that. Agreed? Okay, I got nods. That's the best I'll get. I'll take it. We got yeses. So can I do my dotted line thing again? This is a statistically significant result. There is enough evidence to reject H0, and so HA is true. Haven't we proved that chickens of today are heavier than chickens in the past? And everybody agrees, at least to a significance level of 10%. Suppose this exact same question had one change. Suppose the significance level had been 5%. That's the only change. Would this guy be less than 0.05? No. And wouldn't this turn into, this is not statistically significant? Now, do you see, nothing happened to the data. Wasn't it caused by your choice of significance level? Can't you choose 1, 5, or 10%? Now, if you choose 10%, aren't you going to get a lot more statistically significant results? Right? If alpha is 10%, you're going to get a lot more p-values less than 10% than you are going to get p-values that are less than 1%. Agreed? I mean, that's just common sense. So you might think, well, why don't people just use 10%? Because we like statistical significant results. Well, there's another side to this coin. If alpha is 10%, doesn't that mean 10% of all these hypothesis tests tell us a lie, tell us something that's not true? And do you really want to live in a scientific world where only 10% of the things you believe are true are true? Or 90% are true, but 10% are wrong. I mean, I don't think it would be very good if archaeologists thought that the Greeks came after the Romans. That would, that would not be good. I don't think I would want anybody to do anything that's really important with a 10%. Why do 10% get used then? Well, if the thing you're talking about is not going to kill anybody or is not ground shaking, isn't 10% okay? At least it gives you an idea that something's going on, right? More people drink coffee today than the past, or less coffee, whatever it is. Chickens are bigger today than they were in the past. I have no problems with that being a 10%er, right? Alpha can be 10%. This new drug does a better job than the old drug. Don't you want that to be a 1%er? You want that to be, when you say it's true, you want it to be as true as you can do in statistics, right? You can't be 100% perfect, but can't you at least be 99% perfect? Because that's the other side of the coin, right? If I'm 1% chance of getting it wrong, don't I have a 99% chance that whatever I said is really, really true? And that's a much better place. Although I'm a bit unhappy that 1% of all drugs might not be doing as well as they said they did. But, you have to live with compromises. Are we cool with this data stuff? Right? So I'm going to give you a headache. because I think the best way for you to prove to yourself and to prove to me as well, but mostly to prove to yourself, is I'm going to give you two stories, and one of them's going to be a proportion one, and you're going to use your calculator, right? And the other one, if you've got time, is going to be an X bar story. And it start to finish, if you can do it, and we agree at the end, then I feel comfortable about moving on, right? And if we get stuck on it, then it means I really need to spend more time before we move on. So we are going to have a percentage story first. And the percentage story is that the percentage of adult males in Scotland who get drunk in the past, at least once a month, was 75%. Today, we believe that has gone down. So we believe it's less now. So at a significance level of 1%, using a sample of 50 Scotsmen, we found that, what should we do, 35? 30 out of 50 said that they had been drunk in the last month. So is there enough evidence to prove, based on this story, that that's going to happen? While you're doing that, I'll set up the second one. The second one is going to be right. In the past, the average height of basketball players at universities was 68 inches. And we believe today that basketball players at college teams are taller than in the past. And we're going to do this with a significance level of 10%. So there's your two stories. Well, I guess I should probably do the null and alternate. That'll make it clearer. It used to be 68, but now we think it's bigger. It used to be 75% were drunk, but now we think it's less. Okay. I don't know, 5 minutes, and we'll see how it goes. It looks like you might be finished, Daniel. Does that, you can give me a thumbs up? Cool. And Zoe's finished. Anybody on the blank screens that I can't see anything? If you give me a thumbs up if you've done them. Okay, I got one. We'll wait a few more moments. Are we done, Shannon? Looks like you might be finished. Good. Okay, you can, hopefully you've got one of the two and you can catch up while I'm doing the second one. So essentially, if you take what's important, right, or what's necessary, whatever you want to call it, over here. This one's a proportion one. There's our null alternate. We're going to get p-value and then we're getting our conclusion. And so here it goes. I'm going to hit start. I'm going to go over to tests. What number am I looking for to get the thing that we need here? Is it number 1, 2, 3, up to, I guess, 7? Which one of those guys? 5 is perfect. Have you noticed that you get one proportion is z-tests? Do you know, it's kind of, you might not have noticed this, but do you know with proportions, there's no such thing as a t-test? It's kind of nice. Proportions are always z-tests. It's just the way that it's a binomial distribution. There's a theory behind it. But proportions are always z, so you don't have the same choices, but that's fine. In this case here, P0 was 0.75, great. 30 out of 50, right? That goes there. We're trying to prove that it is going down. So that's why I chose the middle one. And then if I hit calculate, the p-value is 0.007. Okay, conclusion time. Is our p-value less than alpha? Is 0.007 less than 0.01? And yes, the answer is it is. I mean, that's a smaller number, right? So it's a yes. My ... now. Isn't this a statistically significant result? And Scotsmen don't get drunk, quite as big a percentage of them don't get drunk than did in the past. We good on that? Right. Oh, by the way, if you ever do, and I'm sure if you're in the nursing, you will see reports on all sorts of things. Maybe, not maybe, when we come to do two proportion one, I'll show you examples where you compare two things. But in this case here, what you're looking at is simply just, it's statistically significant. Very often you'll find that you're told the p-value. So they will say it's statistically significant with a p-value of 0.007 or statistically significant at the level 0.007. That p-value is the crux of everything. That's the guy that makes you say yes or no, right? It's the important one. Now the second one had a set of data in it, right? So it was basically this guy here. And so I'll get out of this one. I think I'm out. I'll hit start. I'll go into edit. And don't you basically just type in the data? In this case, it was, I think, 7 numbers, something like that, 6. And then you hit start and you go over to tests. And which number do we use in this situation? Because we do not know sigma, and 2 is the guy. And right now, isn't it set up with data, so I don't need to change it? It's mu naught as 68, You know it's 68, it's a bit clearer here, right? Put together all the other pieces, L1, 1, we're looking for things less than, so that's good. And then I'll hit the calculate, and I got all sorts of things here. But the important one is the guy that they're calling P equals. And this time the P equals is a kind of disappointing 0.3, isn't it? At least that's what I've got. Did you get the same numbers? I got a thumbs up, we're going for it. So won't the conclusion this time be, is our p-value less than alpha? Is 0.3 less than 0.1? And the answer is no. So don't we have not statistically significant? So this particular survey, whatever you want to call it, didn't come up with anything statistically significant. So we don't know, essentially. So there's not enough evidence to reject H, no. And we're stopped. Do you feel comfortable with using the calculator to cut out the middleman? When you come to do some of these homework questions, which I'm going to show you in a second, you will find that a lot of the numbers that I didn't write down, you're asked for. So if I return to this one, you will be asked, certainly for the p-value, but can you see that you're probably going to be asked for x bar and Sx, the standard deviation, right? So the numbers that you need are here as well. The number that is really vital is the p-value, right? That's the one that does everything. But the other numbers are kind of interesting. I mean, I can imagine, I can't remember if they did it, but couldn't they ask you for the t-score? In which case you'd write down negative 0.55. Okay, now let's see what that looks like. Oh, I've got a button up here called switch camera. Ooh, should I press? You know, in the movies, they've got a big red button that says don't press. They probably have it in the submarine, right? Don't press this button because something bad will happen. Oh God, that's scary. It's just me. Okay. That wasn't very interesting. I thought it would do something much better than that. So I'm going to do it the good old fashioned way, which means we're going to go back in and look at our homework and what it looks like. And I'll move you a lot out the way. Now, in question 9, can you see question 9 is based on some data? So won't that be the one where you go into, oh, wait a minute, can you see question 9? Okay, so do you see that's a whole set of data, 5.7 to 6.1. Can you imagine that's just going to be typed into L1? Now, it's a little bit distracting here. Do you see that there's percentages? Do you notice that the average yield was 4.5%? Isn't there a temptation when you see percentages, because 99 times out of 100 it's true, that you're going to go p-value, right? You're going to go proportion test. It's not. It just happens to mean that these numbers are percentage. Can you pretend they're just decimals and forget that they're percentages? So put it into your calculator as L1. Go through the same process as before. And on that menu that I just gave, do you see that you'll find the z-score? Remember in the one that we just did, there's a z-score. You just write that thing down. And then there's a p-value, which happens to be, in this case, it'll be that decimal there. And then you have 4 pictures to pick. 4 pictures to pick. I'm going to zoom out and in here. I will once I darn find the thing. Okay, where have you gone? Oh, you're hiding. I'm going to go back into our white screen and show you. Can you see in this case it's got a t-value, but you can imagine it had a z-score, and you see it's got p-value. Right, if I go back into stats, and I go over to tests, and I go to t-tests, and I just go through everything, do you see that there's a guy at the other side to calculate called draw that we've never used? You see that guy? I'm going to pick him. Can you see that you will now have the picture that they have on that screen that I had a few seconds ago? And so you will look at that picture, then you'll look at therefore, and you'll say, oh, it's the third one, or it's the first one. That kind of cool that he even draws a picture for you. Oh, looking at that picture, is this a left, right, or two-tailed test? What kind of test is this? Just looking at that picture, you should be able to tell. Left, right, or two-tailed?
Left.
Yeah. You see all the shading on the left? If it was right, wouldn't it be a little line over here and they'd shade that? And you might think, what would a two-tailed look like? Can you imagine a line and the right and the left are both shaded, so it's both sides? That's what a two-tailed test would look like. Do you see that shaded guy there? That's your p-value. That's the percentage area. See that shaded area? In this question, in our question, what was that guy? 30%. So in that case, that shaded area is 30%. So if you want to visualize what a p-value is, isn't it the shaded area in your normal distribution, right? The percentage of scores that are less than that, same thing. Are we cool? Right, so jumping around, which I seem to be good at doing today. Does this question now make more sense about how you're going to get the answer? Right. And, well, one of those guys is going to be your statistically significant answer. They just give you it as a choice. And here is your conclusion based in English. Right. Can you see this one is basically the same thing, a whole load of numbers, and you go through the same process. It's a lot of basic, no, I don't want to say basic, it's a same process getting used and used again. I mean, the only difference between this question that I've got in front of you and that one up here isn't the only difference in numbers. It's the same question. So it's just practice, you know. It's not that onerous. We agree 7 or 8 numbers, 5 minutes, you're done, right? It's not going to take you forever. And that is the end of that section. And I don't need that calculator. So we've got 8-1 out the way. Yeah, that's good. I'm going to go in here and hopefully find 8-2. Just checking I've got the right one. Okay. I'm scared to do this, but I need some real estate. I am going to minimize you right now. Everybody can still see me. Yes? Okay. I'm going to move over to the 8-2 and show you. Oh, wait a minute. Can you see 8-2? Can you see this guy here? I'm scrolling through it. This is 8-2.
Yep.
If you look really, you don't even need to look carefully. Doesn't 8-2 look like it's the same questions as 8-1? Mostly because it is. Okay, but I think I should really probably do a couple just to make sure that I haven't missed anything. So I was looking at question 7, so I think I'll stick on that one. Here we go. Question 7 then. I apologize to anybody who is Native American because I'm about to annihilate one of these words. But here goes. Pyramid Lake is on the Paiute. Is that good enough? Okay, that was a miracle. It's on the Paiute Indian Reservation in Nevada. This lake is famous for cutthroat trout. I get this impression that there's trout with razors that jump out and attack the fishermen. I mean, cutthroat, I mean, okay, whatever. Suppose a friend tells you that the average length of cutthroat trout in this Pyramid Lake is 19 inches. Well, you know, fishermen always exaggerate, right? Oh, I have a really bad joke. Did you hear about the one-armed fisherman? He caught a fish this big. That was bad. I should cut that out. Okay. Now, in this case, 19 inches. However, a survey reported that a random sample of 46 fish, that it came out as 18.6 inches. So that's basically our sample, right? 46, 86 inches. And that the standard deviation was 3.1, right? So they're giving us the same story. And we are going to find out, is there enough evidence to prove that the length of cutthroat fish, or the weight is it? So weight of cutthroat fish is less than 19 pounds. Now I'm looking at the raw data here. The prediction is it's 19. The data suggests it's maybe 18.6. At least isn't the data suggesting it's less than 19. But is that statistically significant, right? So here goes. What is the significance level? Well, actually the answer is there, but can you see where it came from? There. Which one of these is a null and alternate? I know they've told you this one, but let's see why it's the case. Is it the null hypothesis that the mean was 19 because of that? And is it the alternate that it's less than 19 based on that bit there, right? Great, it's basically taking us through the steps. What sampling distribution will you use? Use a t-distribution. Why? Isn't sigma unknown in this story? See if they had said up here somewhere, oh, and by the way, sigma is 4. Right? Just for argument's sake. Wouldn't you use the Z one and not the T one? If sigma is known, use Z. If sigma is unknown, use T. That's a little mantra for you, right? If sigma is known, use Z. If sigma is unknown, use T. And then they hit you with this fella here. And evidently, this is going to be the T-score. And a weird way of doing the p-value. So I'm going to have to kick out here for a second and show you what they, or how they did what they did. Okay, on the calculator. Can you see yourselves right now? Oh, so do you just see 2 pieces of paper? Oh, because I've been minimizing you lot a lot because I thought it was covering up my real estate. Evidently, I can stick you in a corner and it doesn't matter, right? You don't see it happening anyway. Okay, back to the storyline here. Clear this stuff out the way. We're going to take this data and we're going to go straight in to stats. We're going to move over to tests and we're going to do a t-test because sigma is unknown. Enter. Now, do you see in this case it's got data, but right next to it it's got stats. Can you see the only difference here is that we're going to use the stats menu Because they didn't tell me the weight of the 48 fish, didn't they? They didn't tell me that. Didn't they just tell me the mean and standard deviation in the story? So, mu naught in this story was 19 pounds. X bar was 18.6 inches. The standard deviation, it's in the story, was 3.1. The number of fish was 46. Do you see where all those numbers, weren't they written down in that story if we looked for them? Right, every single one of them. Now, are we trying to find evidence that it's less, different, or more than the 19? Which one was this story based on? Evidence that, right. So actually it's set up, right? It's the middle one. And then can't I go to calculate? And if you want to know the t-score, do you see it's negative 0.875? Can you trust me that's exactly what that screen has? Now, I don't like their p-value thing, but that's fine. Do you see this p-value is roughly 19%, right? 0.19. They didn't have a box where you put in the p-value. What they had are 5 choices. And the choice that I'm picking is the 4th one. P-value is between 12.5 and 25%. Would you agree that this number here, right, is between 12.5 and 25? I think that question would have been so much easier if they just had a box and you typed in 0.193. But if the book wants to say, just give me the interval for p-value, then that's fine, right? Can you imagine that the next time the p-value is 0.04? Won't there be one of the 5 intervals that'll have 0.04 in it and you pick that one? Right, so we'll just do it that weird way. Now, they give you a little picture. Can't we just go back to that menu and hit the picture thing and it'll draw it for me and it'll be one of the 4 and we'll pick it? So that's easy done. And then they finish with, is this fella statistically significant? Is this p-value of 0.19 less than 10%? Nope. So don't they just say it's not statistically, we fail to reject it, is the phrase that they use. At the 0.05 actually, not at the 10. So at alpha equals 0.05, we fail to reject it. That's going to be the box that you pick for that. And that means there is insufficient evidence to conclude that the average fish is less. Right? We just don't have evidence for it. So it's pretty much doing exactly what it did in 8.1, right? They're just doing it their own unique way to write down the answer, right? It's not that the answer is different. They're just kind of putting it together in their own way. That's what I'm saying. Does that seem reasonable? Right. So let's just go back, hopefully one last time, and see what a few more of those guys look like. And with a bit of luck, that will be, actually, I'm going to take out the answers because they take up a lot of space and they're really quite distracting. What do you do if you're attacked by a group of clowns? Don't know? Go for the juggler first. I think Kerry's in pain. Did you like that joke, Kerry? You don't know if you like that joke. It looked like the first reaction was that it was that bad, it was funny, but maybe the second reaction was it was just really bad.
It was funny, but clowns are creepy, so.
Oh, God. I have a niece who's scared of clowns. She truly is. And I think part of that is, do you know that I can't remember because I don't watch horror movies, but isn't there a group of horror movies where clowns attack people? I mean, it's like, you know, like Jason 42, you know, it's like there's Clown 1 and Clown 2. Evidently, she watched that movie and ever since then she's been freaked out. With clowns, I don't care about clowns. They don't bother me. Which is another thing. Do you know, this is me being sexist, but I think it is true. My sister Mary is terrified of creepy crawlies, spiders in particular. They freak her out. Wasps as well freak her out. And I have came to a totally unscientific proof. All her daughters, actually, and her son, although he doesn't like to admit it, are freaked out by the same things. And I know, this is my theory, when you're a little kid and your mum sees a spider and she panics and rushes around like it's, you know, a clown with a razor blade, won't the child pick up a vibe that this thing is scary? So it's mother's fault for making their kids propagate the I'm scared of scary creatures, insects and wasps. So if any of you are scared of them, blame your mum 9 times out of 10 and blame your dad 1 time out of 10, because I think that's probably the ratio. Olivia, are you scared of spiders?
No, I actually have a scorpion.
So you did not have a mother who was terrified of spiders.
She's Australian, so.
Does that mean she's terrified of spiders or not?
No, she just.
That's just, if you see them every day, you can't be terrified. Kerry, are you scared of spiders? Is your mum scared of spiders?
No,
Is your dad scared of spiders?
no.
Shit, that theory is out the window. I did say shit there, right? Just in case you heard something else. Right. Okay, distracting because my brain is freezing up and I have to do things to just get my focus back. Can you basically see that you're just going to get a whole load of stories based similar to the one we just did? So you're just going to get lots and lots of practice at the same all. So I'm seeing if there's a proportion one at the end of this. There may or may not be. Doesn't look like there is. Do you want me to do one more of these, or are we comfortable just scrolling through them? Do you want to see another one from start to finish, or are we good? You don't? Okay, I don't blame you. I'm just, last check. Right, every single one of 8.2 is basically going to be like the one question I did. I don't even think they had the imagination to mix and match the questions. I think they just took the same question and just changed the story at the top, right? So hopefully that means that the questions, although they take up a lot of real estate, they don't take up a lot of time. So I'm hopefully, 5 minutes each question, boom, it's done, right? It's always risky, but can I call this one done? Okay. Feel like I'm at an auction house. Last chance. I'm about to hit the gavel. It's gone. Well, let's get a move on. We might as well use the time that we've got at least to get a good head start on the next one. Because if I can get that done. Oh, by the way, your homework is 4 sections, and then you've got 9.1 and 9.2 that are due on Monday. I've opened them all up, so all homework is due on Monday. So that gives you the flexibility to, get it all done by Saturday if you wanted, and then that gives you a couple of days to get ready for the final. So it's up to you how much time you can do. So if you can batter through your homework quickly, then you'll be done, right? 9.2 is the last homework assignment. Once that's out of the way, you are done. And all of them should be open. Just to make me feel better, can someone quickly zoom into WebAssign and confirm the 8.1 to, okay, we got to confirm. So it's there. They all should say due by whatever, Monday is the 10th, I think, isn't it? Right. So you get these guys out of the way, the better. To try and help with that process, I'm going to move on now to our third out of our 4 sections. And this one is, oh, I'm going to have to move you around again, is 8.3. This is not what I thought. Okay, I gotcha. Do you want the good news or the bad news? Which do we want first?
Bad news.
You're going to get bored. What's the good news? 8.3 we've already done. It's just some more proportion questions now. Right? So for completeness sake, I'm going to pick one at random and we'll go through it just to show you, you know, because they do it kind of their own little way, just to give you the gist of it. And we're going to use the calculator and we're going to get all the usual stuff from that. And hopefully if I show you one, you'll say, let me just scroll in case they did something at the end that I'm not aware of. No. So there's 10 questions, and apart from the first two, which we'll talk about right away, they're really regurgitating hypothesis tests with one proportion. So I'm going to pick one and put you over here and close that, and open this, and oh, we got some chat. Oh,
That is
nothing.
totally irrelevant.
Yeah, nothing to do with me, just in case it's a question. Evidently, someone knows someone who's becoming a 4th grade teacher. By the way, teaching is fun. I don't know if any of you have got that as a career. I think it's fun. I have a hilarious time. I don't know about you lot, but I definitely have fun. Just telling you lot bad jokes is fun. So go figure. Okay, let's get the first questions. Actually, there's more than 2. It was 3, but we can figure that out, right? To use the normal distribution test, P, these conditions have to be met. Can you remember that's the same conditions that you need if you want to get a confidence interval and so on, right? Okay. Now, does the value of P, do you get it from the H naught or do you get it from the sample? And do you see that you get it from H naught? Isn't that where we got it every one today? So that's just something I already knew is done. Now, okay, consider the binomial experiment. That's just a fancy name for asking people a question and they say yes or no. Binomial means there's 2 answers, right? They can say yes, they can say no. That's all it's like. To construct a test for a proportion P, what value do we use for the Z value in the sample test statistic? Now, if you look at all of these guys, that's the only one that actually gets used. Isn't that P hat? Isn't R over N P hat? And our calculator, unfortunately, don't they call it X over N, but what the heck, it's the same thing. In general, if a sample data are such that the null hypothesis is rejected at the 1% significance level on a 2-tailed test, is H not rejected at the 1% significance level for the corresponding 1-tailed test? And that is a good question because I didn't talk about that. If you do a T-tailed test, p-value has to be smaller than alpha. If you do a 1-tailed test, the area is also smaller than alpha. Well, actually, that's not what I wanted to hear them say. Do you know in a 2-tailed test, because there's 2 sides, you're meant to double the value of p-value. So p-value gets doubled. So see if you do the calculation by hand, the p-value gets doubled. If you do it by the calculator, it's done that for you, so you can just leave it alone. So if it's a 2-tailed test, and you were doing it by hand, which probably none of you are going to do anymore, because now you know the other way to do it, you would double it. If it's done on the calculator, they've already done that for you. So, oh, by the way, I can imagine this happen. Can you imagine you did it by hand and then a 2-tailed by hand, and then you did a 2-tailed on the calculator, and you looked at the p-value and you wondered why one of them was twice as big as the other? That's because when you did it by hand, you forgot to double it. And you might say, why do you double in a two-tailed? Remember, a two-tail's got two sides. You're only finding this side, but you have to double it to account for what could have happened, which was the other side. So that's the logic behind why you double. But since you're going to do it by calculator, it doesn't matter. But I'm just going to pick one of these. As I scan through, do you see it's the same questions? That's why I said you're going to get bored. There's not a lot of variation here. Okay, let's stop at 7. It's as good a question to stop at as any, and just take us through the stages. Women athletes at certain university have a long-term graduation rate of 67%. That's not good. Women athletes, only 2/3 of them graduate. But if you turn that on their head, doesn't that mean 1/3 of them drop out or fail?
Is this because Santiago was a different shade of brown here?
Say that a bit again, Chloe.
Mr. Jones.
Chloe, had you a question, or was that just some background sound? Okay, I'll mute everybody just in case we hear something that we're not meant to hear, right? So if you forgive me, I'll zoom back to this story then. Okay, so to me that's disappointing. I know being an athlete at university has lots of advantages. Don't you tend to get scholarships, and therefore you probably can get your degree for free or darn close to it? Isn't the negative side that they expect a high commitment from you in time? They want you to do training, 4 hours a day, or they want you to turn up for weekend meets, and they want you to do this and they want you to do that. Could you imagine if they're really severe on your time? Couldn't that eat into your ability to study for your exams and be successful? So I'm just wondering if that's the reason. So if any of you are looking at an athletic scholarship, that might be something you want to take into account. Right, over the past several years, a random sample of 40 women athletes at the school showed that 23 eventually graduated. Does this indicate that the population proportion of women athletes who graduated from university is now less than 67% and use a 1% level of significance? Okay, so I'm going to take the gist of that story, do it on paper with the calculator, and then once I've got all the answers, we're going to return to this and show you where the numbers go, okay? Hopefully that makes sense. So this is a story about women athletes, and I still have information. So in the past, it was 67%, right? They want to do a significance level of 1%. And we took a sample, and that sample was 23 out of, darn it, where I can find it, 40. So our null hypothesis and our alternate hypothesis. Isn't the null always the data from the past? So that guy is going to be H0, and he comes from here, right? In this story, they ask us, is there enough evidence to show that that percentage has declined, right? So, agreed? The null is it's still 67% pass rate. The alternate is it's got less. Now, if I do a quick calculation on that, let's find out what that is, just out of curiosity. 23 divided by 40. Ooh. Not good. Well, it's what, almost a 10% decline. Now, that might not be statistically significant because it is a small sample, isn't it, 40? Right. Small samples don't always give you statistically significant results. So I'm going to go in now and get all the other numbers that we could possibly want. I'm going to hit start, I'm going over to tests. Now, which number do we get or use to do this fella? And yes, agreed, Stacey, 5. Now, in this case here, 0.67 goes there. There was 23 out of 40. And we were looking for evidence, weren't we looking for the middle one, that it was less than P0? And I'm going to do the draw thing first. Can you try and remember that picture? Can you see it's a guy shaded to the left, right? Because one of the answers is going to be that guy. So try and remember him. I'm going to zoom back in. I don't need to change the data because it's the same data as it was a minute ago. And here is everything that you could possibly want to know, and probably some stuff you don't really want to know. So the Z is negative 1.28 roughly. The p-value, oh, goodness gracious me. That's not good. P-hat, we already know it, but I'm putting it in now. Now, a 1% significance level, is the p-value less than alpha? Is 0.1007 less than 0.01? Would you agree that that is a clear no? So this is not statistically significant. So that means we do not reject H0. Now, all this stuff that's here is now going to get transferred into the answer in WebAssign. So we may have to tweak it a little bit, but can you know, when I pick up numbers, I'm going to be using these guys here, right? So when I say this goes there, it's because I have it in front of me. Even if you can't see it anymore, that's where I'm doing it from. So I'm kicking in here. And well, I'll leave it now. The answers are here, so we can do it pretty quickly. But let's see where they come from. What's the significance level? Well, wasn't the significance level 1%? So that's where that went. So you would type in 0.01. Agreed? State the null and alternate. Wasn't that my null and alternate that I had on the paper? What sampling distribution do we use? That's the guy that we're using. Do you know proportions? You always use a Z, standard normal. There is no T, so don't even pick it. And the other choice was this one. But which one of those two do you always use? Don't you use the one that has that true? Shouldn't you do a quick check? Are the conditions met? And that's this. Now, when you looked at your calculator, that guy was exactly negative 1.28, and I have this written down. Wasn't that guy the scary 0.1007? Can you remember what picture? Wasn't it that picture there? Remember I said remember the picture. It's a bit annoying when the answer's there, but if the answer hadn't been there, hopefully you would have picked that one. Right, let's get the last two boxes. One of these four answers is how you would phrase it. Do you see not statistically significant? So doesn't that only give us two choices? It has to be that one there or this one here. you fail to reject the null hypothesis, right? The other choice is we reject the null hypothesis. If it's not statistically significant, don't you fail to reject the null? So that's why it's this one. If it's not statistically significant, you can't really say anything, right? I wrote down here, we do not reject H naught. Isn't that the same as saying fail to reject H naught? That's just a phrase they're using. And in English, there is insufficient evidence at the 1% level to conclude that the women's athletes who graduate is less than 67. So statistically, I'll make this story up. Let's suppose that women athletes decide to sue their university because they failed. And they're going to cite as their reason that they failed is that you asked too much of me and I was being set up for failure. How can I pass my engineering degree if 80% of my free time is taken by, training for track and field, right? And they would come and they would say, well, what's your pass rate? And let's just say the university's pass rate is 67% for everybody, just for argument's sake. If we did this test, wouldn't the result come back? You are not that unusual. Okay, you are low, but that's just randomness. You could have just been a bad year, right? Where not as many pass, and next year is going to be 69% of you pass, right? It's an average, right? It changes every year. And so you wouldn't be able to win that in the court of law. Now, court of laws are different. Do you know there's criminal procedure cases, and then there's, I think you call them civil. Do you know when you sue someone, it's civil? Do you know what the rule is for criminal? You got to have the vast majority of evidence, right, against the guy. Do you know what the ruling is for civil procedures? It's a 50-50. You only need to be 51% compared to 49. Essentially, you just have to prove that you're likely to be right more often than the other guy, right? It's a two-way argument. I'm right. No, you're right. That's essentially how these things work. So maybe that's why people sue everybody so much in America, because I guess you get lots of money if you, well, you don't. Don't the trial lawyers get lots of money and you get what's left? So, a side issue. Are we cool with me going through that one? Because 2 and 3 are only one difference. Isn't 2 going to use X bars and it's going to use the menu that's to do with means? And isn't 3 going to be doing proportions, and it's going to be using the one proportion t-test, right? One proportion z-test, I should say. Agreed? Your time is valuable. I think this is a natural stopping point, because I know the next one is big. It's only one section, but it's got a lot of stuff in it. I'll give you a heads up on what it's going to be. The last thing that we're going to do in hypothesis testing is testing to see if 2 different groups are different in some way. So, give you an example. We're going to have women and men. And women, what percentage of you like sci-fi movies? And men, what percentage like sci-fi movies? And we're going to do a hypothesis test that goes something like this. Is there enough evidence to suggest that men like sci-fi movies more than women? Or less, whatever it is, right? So it's going to be a hypothesis test with 2 proportions, 2 different groups of data, and we're butting heads together to see